Hello, everyone. My name is Tianjian. I'm a software engineer at Google. And Yifan is the co-author of the work. We are presenting the case studies on accelerating scientific computing applications with TPUs. First, I would like to briefly introduce the motivation of our work. As we all know, the recent success of deep learning has spurred the new wave of hardware accelerators. One such example is Google's Tensor Processing Unit, or TPU. TPU has the strength in tensor operations. In witnessing how scientific computing applications benefit from the advancement of hardware accelerators, it's tempting to ask whether TPU can help us with scientific computing applications. And we seek an answer to this question through the case studies. The figure on the right is an overview of TPU v3 hardware architecture at the chip package level, the board level, and the system level. TPU is designed as a coprocessor on the I/O bus. It has 4 chips per board and 2 cores per chip. Each board pairs up with 1 CPU host. For a TPU v3 part, a total number of 2048 cores are connected. If we can formulate the problem and design an algorithm in accordance with TPU architecture, it indeed achieves good accelerations by running the scientific computer applications on TPUs. MXU, or the matrix multiplication unit, provides the bulk of the computing power, with 16K multiply accumulate operations per clock cycle. Based on that, we design the building blocks of an application as much as tensor operations. As for the interconnect topology, it's a 2D torus for TPU v3. The interconnects are dedicated and on-device. They are high speed and low latency. The interconnect do not go through the host CPU or any networking resources. The interconnect topology affects our decision of data decomposition and communication strategy for parallel computing with TPUs. To achieve high parallel efficiency, we need to do 2 things. First, select the highly parallelizable methods. For example, the alternating direction method of multipliers, ADMM, and the conjugate gradient method, CG. Second, we need to design an algorithm to localize the tensor operations as much as possible. As for the memory, TPU uses high bandwidth memory. This guides us to determine the shape of the operands in the localized tensor operations. Now let's move on to the case studies. For the case studies, we cover Fourier transform, linear solver, and numerical optimization. For the Fourier transform, we have DFT, the discrete Fourier transform, FFT, the fast Fourier transform, and NUFT, the non-uniform FFT. For the linear solver, we use the conjugate gradient method, CG, to illustrate the purpose. And for numerical optimization, we select the alternating direction method of multipliers, ADMM, and we also combine them in the application of medical imaging. Now let's look at our first study, DFT on TPUs. Fourier transform is critical in many scientific and engineering applications. For example, time series and waveform analysis, convolution and correlation computations, solution to the partial differential equations, and density function theory in first principle calculations. The general form of DFT is shown in the first equation, where xn is the input. DFT has a matrix form, which is written as capital X equal to capital V X. V is the van der Waals matrix. The matrix form of DFT can be generalized into higher dimensions with the Kronecker product. The example shown here is a 3D DFT, where VG, J equal to 1, 2, 3 are van der Waals matrices corresponding to 3 dimensions. It can be seen that DFT is essentially a tensor operation between the Van matrix and the input. So the problem is generalized into the one that how to compute the tensor contractions efficiently and in parallel on TPUs. To achieve that, we design the one-shuffle algorithm. There are three advantages of the one-shuffle algorithm. First, tensor operations are localized on individual cores. Second, communication takes place on the same direction along the interconnect network. And third, it achieves high parallel efficiency. Let's see an example of 3D DFT. So in a 3D DFT, we have 2D Van matrix and a 3D input. We partition the input along all three dimensions. So each core contains a 3D block of the input. We also slice the Van matrix along the first dimension. So each core contains a row slice. The Van matrix and the input contained on the same core are highlighted with the same color. In the one-shuffle scheme, as the first step, we do a tensor contraction between the Van matrix and the localized input. This operation is local. And then we shuffle the data along the first dimension. After that, another tensor contraction, and again, shuffling the data until information of all cores along the dimension is propagated. The one-shuffle algorithm uses one ISAM operation and one collective permute operation. The ISAM operation, or tensor contraction, is localized, whereas the collective permute operation is responsible for the communication among the cores. Now let's look at the strong scaling analysis. This is a 2D DFT example. The problem size is fixed at 8K by 8K. We first use 2 cores and keep doubling the number of TPU cores being used up to 128 cores. We define the ideal time as a reference, which is from the linear scaling with respect to computation time with 2 cores. From the figure on the right, it shows that a close to linear scaling of the total computation time is achieved. The scaling of the time spent on ISAM is linear because the tensor contraction are localized within the cores and performed completely in parallel. This is another example for DFT. It's a 3D DFT. The problem size is fixed at 2K by 2K by 2K. We use up to 256 TPU cores. We also define the ideal time for a reference, which is from linear scaling and with respect to 32 cores. It can be seen that a close to linear scaling is also achieved for the 3D DFT. The computational complexity of DFT is n squared for an n-point transform. But DFT handles non-uniform sampling without any modification to the implementation. People normally use FFT if input is uniformly sampled. FFT is based on the Kulitakis algorithm, which has the computational complexity of n log n for an n-point transform. Let's see how we can compute FFT in parallel on TPUs. The FFT formulation starts with the same equation of DFT. We rewrite the global index n as n equal to PL plus beta, and P denotes the number of cores. Further, we can use the definition of global index and rewrite the equation into one that consists of 2 terms, a phase adjustment term and the transform term. We first compute the transform with the Kulitakis algorithm, and then apply the phase adjustment. The phase adjustment is performed with the one-shuffle scheme we just described. The figure on the right illustrates the 4 steps of the parallel algorithm for FFT on TPUs. First step, data decomposition. We apply data decomposition to the input along all 3 dimensions. Segments are highlighted with colors. And second, we gather the input, making sure that the segments of the same color are on the same core. This is to ensure an in-order transform. Third, transform is performed locally on individual cores. Last, we apply the phase adjustment through the one-shuffle scheme. Next, the strong scaling analysis. For FFT, we have a 3D FFT. The problem size is fixed as 2K by 2K by 2K. We start with 16 cores and all the way up to 128 cores. We also define the ideal time of linear scaling for reference. The ideal time is defined with respect to the computation time of 16 cores. From the figure on the right, it shows that a close to linear scaling is achieved in terms of the total computation time. In addition to the strong scaling analysis, we also provide a few examples on the full TPU pod. The problem size varies from 1K cube to 2K cube and all the way to 8K cube. And the reported runtimes are for complex transform. As a reference, the runtime of a real transform, a real FFT, for the problem size of 8K cube on CPUs is 5.36 seconds. The numbers are from 48 nodes of Fujitsu cluster. It's converted from 10 teraflops reported by Takahashi in the year 2019. Again, this is a real transform. A complex transform is about 4 times the arithmetics and 2 times the communication compared to the real transform. Now let's move on to another case study of a NUFT on TPUs. Sampling approaches in many applications are non-uniform. This is particularly true in medical imaging domain. The primary goal of non-uniform sampling is to reduce the data acquisition time. In order to retain the computational complexity of FFT, n log n for endpoint transform, and at the same time handle non-uniformly sampled data, we need a NUFT, the non-uniform FFT. As shown in the figure, a NUFT consists of 3 components: apologization, FFT on the uniform grids, and interpolation. Let's see how we can distribute the computation of NUFT on TPUs. For parallel computation, we need a partition. Figure on this slide shows the partition of a 2D image into patches. We, on purpose, leave an overlap of size of kernel width. The kernel is used in both apologization and interpolation. And after that, we patch the kernel coefficients with zeros. The dark blue color shows the non-zeros after padding. And then we shuffle the kernel coefficients. Before feeding the data into the computation, we have a load balancing, and each core contains partial k-space information. The most expensive operation in NUFT is interpolation. We formulate the interpolation operation as tensor operations, which are highly efficient on TPUs. Figure on the right is a flow graph of the operations in forward NUFT. It can be seen that the interpolation in forward NUFT contains a tensor contraction, a matrix multiplication, and a reduced sum. Similarly, the interpolation in the adjoint NUFT, or the inverse NUFT, is also formulated as tensor operations. Figure on the right is a flow graph of the operations in adjoint NUFT. We first scale the coefficients with k-space data, and then perform a tensor contraction with a Boolean mask. Now let's look at the performance of NUFT on TPUs. We provide a table in this slide. The table presents the computation time of forward NUFT on 3 types of hardware: CPU, GPU, and TPU v3. From the computation time, it's shown that TPU achieves significant acceleration compared to CPUs, and the runtime on TPU is comparable to that of GPU. Now let's look at the scaling analysis. For the scaling analysis, we use image of size 512 by 512 over a sampling factor of 2, number of points in K-space 0.4 million, and number of TPU cores from 2 all the way to 128. Figure on the top, the scaling in terms of speed up is close to linear. And we also did experiment of computation time with respect to number of partitions per dimension. The number of partitions, 16 along each dimension on the image, achieves the best performance in terms of runtime. Now let's move on to the next case study. In this case study, we implement the conjugate gradient method, CG, and the alternating direction method on multipliers, ADMM, on TPUs. Together with DFT, we apply them in an image reconstruction problem for magnetic resonance imaging, MRI. MRI is a powerful medical imaging modality. It's non-invasive. It has excellent soft tissue contrast and high spatial resolution. MRI has revolutionized the field of medical imaging since its invention in 1970s. The reason we choose this as a case study is because MRI is important and competition in MRI image reconstruction is the new bottleneck. For the following reasons, MRI data acquisition speed is approaching the physical limits. Further acceleration MR requires breaking the Nyquist sampling criteria by sparse sampling and constrained image reconstruction. However, the state-of-the-art MR image reconstruction methods often build upon large-scale, iterative optimization algorithms with extensive usage of non-uniform Fourier transform. It's computationally feasible for practical clinical use. Let's see how we can address the competition bottleneck of MR image reconstruction with TPUs. The MRI signal model is a Fourier transform. In compressed sensing, one reconstructs an image from the undersampled K-space data by solving an optimization problem. The optimization problem has two terms, the data fidelity term and the sparsity constraint. As mentioned before, we use ADMM, the alternating direction method of multipliers, to solve this large-scale, convex optimization problem. ADMM consists of 3 updates in terms of the primary variable, dual variable, and auxiliary variable. The update of the auxiliary variable has a closed form. The update of the primary variable, known as the complex image intensities, can be considered as a regularized least square problem. This problem can be solved iteratively by using the conjugated gradient method. That's how CG is useful in this application. For parallel computing, we apply the data decomposition to the K-space. 2 operations are repeatedly called in the iterative scheme, a DFT and sparsifying transform. The DFT operation and its adjoint are formulated as tensor contractions. The sparsifying transform operation and its adjoint are formulated as convolutions. Both tensor operations and convolutions are highly efficient on TPUs. This slide shows the communication strategy, where we need sending or receiving data among TPU cores. As I mentioned before, ADMM has 3 updates per iteration. The update of the auxiliary variable is local. The update of the dual variable is also local. The update of the primary variable is through the CG solver, which requires communication. The communication is done through cross-replica sum, which is to sum the partial images across TPU cores, such that all cores start the new CG iteration with the same image. This is the only place we need communication. Before diving into the performance benchmark, let's use one example to show how accurate the implementation on TPU is. We use the phantom as the example. The k-space data were retrospectively undersampled with an undersampling factor of 8 to demonstrate the capability of compressed sensing in accelerating MR. The total number of k-space measurements was 19,968. We have 12 cores in total. The images were reconstructed on a uniform grid of size 128 by 64. The relative difference is about 1% for the voxels within the phantom, which is considered as satisfactory. The strong scaling analysis was adopted to understand the parallel efficiency. For this, and we also provide a table of runtimes. And we use the phantom data. The phantom data were acquired by using 804 radio readouts, each with 1024 samples. The fully sampled k-space data were then retrospectively undersampled by a factor of 8, resulting in a total number of 1.2 million k-space measurements. Again, we have 12 cores. Runtimes on CPU, the Intel Xeon 8-core processor, and then GPU, NVIDIA V100, are provided as a reference. I need to mention that the implementation on TPU uses DFT, whereas the implementations on CPU and GPU use NUFT. But even though DFT has higher computational complexity than NUFT, we still see accelerations on TPUs. This is good news. In addition, from the figures on the right, we see that close to linear scalings on TPU are achieved. Through the case studies, we explore TPU for scientific computing. The case studies include Fourier transform, a DFT, FFT, and NUFT, linear system solver, CG, numerical optimization, ADMM, and their applications in medical imaging. We formulate the problem and design an algorithm in accordance with TPU strength in tensor operations and its high-speed interconnect network. We see that TPU achieves good acceleration for these scientific computing applications. This concludes my talk. Thank you for listening. Bye-bye.